Suppose you want to arrange a night party in a garden for your friends and relatives, and you wish to have a lamp which is vertically above the center of the garden. So, what should you do to have the maximum possible illuminance from that lamp? What should be the position of that light source? So, this is what we're going to talk about in this video. It appears that this question needs calculus. With this, I welcome all the viewers to the Math Exploration Tour. So here is a problem which was asked in the entrance exam to Indian Statistical Institute in 2017, and it was the 17th problem in part A of the entrance exam paper. So let us see what it asks. So the problem says a circular lawn of diameter 20 meters on a horizontal plane is to be illuminated by a light source placed vertically above the center of the lawn. It is known that the illuminance at a point P on the lawn is given by the formula I equals C sine of theta by d square for some constant C, where d is the distance of P from the light source and theta is the angle between the line joining the center of the lawn to P and the line joining the light source to P. Then the maximum possible illuminance at a point on the circumference of the lawn is. So as you can see, here is the diagram. There is this circular garden which I have drawn over here in color red, and there is this lamp which is placed vertically above the center of the lawn if you visualize this in 3 dimensions. So let us start. Now the first thing we need to do is decode this problem part by part. So let us write down what is given. So it is given that the diameter of the garden is 20 meters. So we can as well say that the radius is going to be 10 meters. Now, it is known that the illuminance at a point P on the lawn is given by this formula. So let's mark the point P on this lawn. So let us say it's here. And the illuminance I is given to be C sine of theta over d square. Let's draw the radius connecting P to the center. So let us say the center is this here, as the lamp is vertically above the center. So now we are going to connect these points. Once like this, and then another joining the light source to the point P, and another line joining the light source to the center of the garden. Let's say the center of the circle is O, and this is N. So now what else the problem says? The problem says that D is the distance of P from the light source. So this distance must be D, which is LP. So LP must be D. And OP, remember, is the radius of the circle, so it must be 10. What about the angle theta? Theta is the angle between the line joining the center of the lawn to P, which means it is this line, center of the lawn to P, this line OP, and the line joining the light source to P, that is this to this. So then this must be theta. Now, we have all the values given to us, and it's about using those values. Is there a relation you can find between theta and D? Let us figure that out. So we will now visualize the triangle LOP, which is in fact in 3 dimensions, even though the figure has been drawn in 2 dimensions. Visualize the triangle LOP. It is actually a right angled triangle because LO is perfectly vertical because L is directly above O as per the definition. and OP is perfectly horizontal because it lies on the circular garden. That means that triangle LOP is a right angle triangle. And once you see a right angle triangle as well as some sides and angles, the first thing you can see is trigonometry. So let's do that. So by applying trigonometry in triangle LOP, you get that cos of theta equals adjacent, which is 10 OP, divided by the hypotenuse LP, which is D. What we want to do is to maximize illuminance. As we can see, I equals C sine theta over D square. C is a constant, but I is varying both with theta and D. But we need to express it in terms of one variable now, because we know the relationship between theta and D as cosine of theta equals 10 by D. Now, from this relation, I want to eliminate D and keep just theta in the expression for illuminance. So what I'll do is D is 10 by cosine of theta, which is seen over here by rearranging. And so D square is going to be 100 divided by cos square theta. And here is 1 by d square because I is c sine theta times 1 by d square. So what I'm going to do is I'm going to write 1 by d square as cosine square theta divided by 100. Now, since I know that I is c sine theta by d square, and 1 by d square is cos square theta by 100, I is nothing but c sine of theta times cos square theta by 100. Notice that c by 100 in the expression for illuminance is obviously a constant. So now what I need to do is to maximize sine of theta times cosine square theta. So I'm going to consider a function f of theta equals sine of theta cosine square theta, which I have to maximize. And when it comes to maximizing a function's value, then we need to resort to calculus. There's this concept of calculus known as maxima and minima, which allows us to find the local maxima and local minima of a function f in a given interval. So here, obviously, theta must vary between 0 and pi by 2. You can notice that here because if theta is 90 degrees, then you cannot connect L and P because it becomes LO becomes parallel to the line joining L and P, which means they will never intersect. So it must be lesser than pi over 2 and also must be greater than 0 for quite obvious reasons because if it were 0, then the light source would be in the plane of the garden, it wouldn't be above it. So once we know the interval in which theta belongs, we need to maximize it in this interval. So now, first thing we need to do to maximize this function is to find the points where the derivative is equal to 0. Before we do that, we need to find the derivative. So f prime of theta, what we denote for the derivative of f of theta, that's going to be using the product rule, sine of theta times the derivative of cosine square theta, which by the chain rule, remember, is 2 cosine of theta times the derivative of cosine of theta, which is minus sine of theta, plus second function cosine square theta times the derivative of sine of theta, which is cosine of theta. So now I could take cosine of theta common. and write it as cosine squared theta minus 2 sine squared theta. Now I can do one more thing, because if I divide by cosine squared theta in this part like this and multiply by cosine squared theta again, then we notice that f prime of theta becomes cosine cubed theta times 1 minus 2 tan squared theta. Now it's pretty clear that the point where f prime of theta equals 0 if theta belongs to 0 to pi by 2 is either when cosine of theta equals 0 or 1 minus 2 tan squared theta equals 0. But if cosine of theta equals 0, it's only possible if theta equals pi over 2, but that's not possible because theta belongs to 0 to pi by 2, excluding both 0 and pi by 2. That means that we must have 1 minus 2 tan squared theta equal to 0, which means tan theta must be equal to 1 over square root of 2. And how do we know that whether it's a point of maximum or a minimum? There are two ways to do it, the first derivative test or the second derivative test. So if you know how to show that the point, this point where tan theta equals 1 over root 2, whether it's a point of maximum or minimum, you can let me know in the comments below. So that's one thing we found out, that there's a point of maximum, in fact, at tan theta equal to 1 over root 2. That means that for maximum illuminance, we must ensure theta such that the tangent of this angle is 1 over square root of 2. But what the problem asks is different. It's asking the maximum possible illuminance, that is the value of that illuminance. So for that, we just need to substitute the value of theta in the expression for illuminance. What we found for illuminance was I equals C by 100 sine of theta cosine squared theta. Now, if tan theta equals 1 over root 2, you can use elementary trigonometry to conclude that if theta is acute, then you can say that sine of theta must be 1 over root 3 and cosine of theta must be square root of 2 over square root of 3. Thus, by substituting the values of sine of theta and cosine of theta, you have I equals C by 100. Sine of theta is 1 over root 3 times cosine squared theta, which is 2 by 3. Thus, the illuminance is going to be C by 150 square root of 3. So this is the maximum possible illuminance at any point on the garden. That's what the problem asks. And if you are intending to practically do it, what you require is the height of the light source from O, that is the vertical height. And that can be easily found out because it is just going to be elementary trigonometry which you're going to use. That is, again, you know that tan of theta equals LO by 10. Since you know tan of theta, LO is easy to find because it's just 10 times tan of theta, which is going to be 10 over 10 by square root of 2. That's the height you require for maximum illuminance. So this was about it in the problem. The intention of this video was to demonstrate how calculus is applied in real life. So for more such videos on great mathematics, please subscribe to my channel. Thank you.